And we love to have conversations around fundamental sciences as well. And today's topic is on active matter studies by perhaps one of the founders of this part of physics that we are talking about. If you open Wikipedia and look for active matter studies, you will see that out of the 15 or 16 citations at the end of the Wikipedia page, 3 of them are Professor Sriram Ramaswamy, who is our speaker today. Professor Ramaswamy completed his Bachelor of Science degree in physics from the University of Maryland, and then completed his PhD in theoretical physics at the University of Chicago, and his postdoc work at University of Pennsylvania, and has been on the faculty of the Indian Institute of Science, since then, and also kind of was the director of the TIFR Center for Interdisciplinary Studies in Hyderabad for a brief period. Needless to say, multiple awards. I think Fellow of the Royal Society in itself is a very prestigious thing. But in the Indian context, the Shanti Swarup Bhatnagar Award, the Infosys Prize, and the Firodia Award for Physics, I think are, if you want to just choose and pick and choose 3, those are the 3 that one would choose. Moderating the conversation today, Dr. Vijay Krishnamurti did his PhD at the Indian Institute of Science in Bangalore, worked as a postdoctoral fellow in Germany at the Max Planck Institute, and currently at the International Center for Theoretical Physics in Bangalore, ICTS. They've been, from what I'm reading, they've both been working together on various problems in this area. So I'm sure the interaction will be great. And finally, my colleague, Dr. Sushila Venkatraman from the IIT Alumni Center is also a moderator. To the audience, please put all your questions in the Q&A box, which is at the bottom right of your screen. Do not put it in the chat box because the moderators are monitoring the Q&A box for the questions, not the chat box. So if you want your question unanswered, then put it in the chat box, right? So otherwise, the Q&A box is the best place to get it answered. That's point 1. We will start now with Professor Sriram, talking about his subject of the day, and perhaps we'll have a break in 20 minutes when we will take questions. I think Professor Ramaswamy has structured it with 2 breaks, if I'm not mistaken, but he will have, but the choice is his. He can just move on the way he wants to. With that, Sriram, over to you.
Very much for inviting me to talk in this series run by the IIT Alumni Association. So what I'm going to tell you about is a sort of physical approach to living matter and to imitations of living matter of a wide variety of types, which are shown on this opening slide. Whether ranging from macroscopic phenomena like schools of fish or flocks of birds to subcellular phenomena like this rotating nucleus inside a cell, to artificial imitations of self-propulsion like this little movie on the right, which I'll tell you more about. We'd really love to understand on a purely physical basis the laws that govern spontaneous organization of moving living things in nature, like this cormorant flock above the old building of the TIFR Center in Hyderabad. And I'll try to tell you a little bit in this talk about how we go about this. Okay, and this is, if you like, it's part of a general interest in patterns in the natural world. You can see very, very organized patterns on a big range of length scales, having to do with the physics of systems driven far from equilibrium, both in living systems like this millipede flock at the University of Hyderabad, or in non-living but still out of equilibrium systems like this very beautiful, what you might call a liquid crystalline pattern of clouds in the sky in Hyderabad a few years ago. And so I'll tell you a bit about real and imitation living matter in today's talk. So, collective motion, as you've seen in these preceding slides, can be quite spectacular. And one of the areas in which physicists have got very interested in the phenomenon is actually bird flocks, of which I'm showing you a movie taken by an amateur photographer in Bikaner called Rakesh Sharma, who has these spectacular images and videos of mynas in the evening sky flocking and moving. And the whole thing it's obviously a much more complex system than the simple models that I'm going to talk about today. But it's important to appreciate not only the orderliness of the phenomenon, but also its beauty, which is really why I'm showing you this. Anyway, that's it for images for a while. I also want to emphasize that these phenomena take place, as I said earlier, over a huge range of scales. Similar phenomena of collective motion can be seen if you take little molecular machines that are the responsible for all internal movement and ultimately even for muscle movement in our body. They are called molecular motors. Some of these are called myosin, and people grafted those to a glass slide here, and they sprinkled on them the biological filaments on which the motors walk. So what they've done is they've stuck the motors with their feet in the air, and they put above, sprinkled on this system in a fluid medium, the filaments on which the motors normally walk. So now, because the motors are stuck, the filaments will move. And these were classic experiments that showed that such motors are ultimately responsible for transport and movement in our body, which I'm just showing you here to emphasize the range of scales over which all these phenomena take place. And all of these areas are grist to the physicist's mill as they try to understand the laws of living matter, the mechanical laws of living matter, understanding living systems as a kind of material, okay? Bringing that into the fold of material science and condensed matter physics on scales from subcellular to whole groups of organisms and sort of in sickness and in health, if you like. Now, it's important to know that physics enters biology in many ways, dominantly in two ways though. Information, that is the storage, processing, and transmission of information, whether when something senses and responds to its surrounding, or when you take stored information and accurately transcribe it to make proteins, or when you reproduce a whole organism, or over evolutionary timescales when that information slowly changes because of random events and natural selection. And the other part, of course, is mechanics, since mechanics enters everything. The success of the approach we have taken, we and many other people have taken to the physics of living matter, is to not worry about the information aspect and focus on mechanics. So that's the easier problem, and that's what I'll talk about. Eventually, we'd like to incorporate more complex functionalities, information processing on different time scales, sensing, signaling, replication, maybe even evolution. But for now, we don't do that. Now, the reason physicists enter the part of the game that I'm talking about is that physicists, especially what are called condensed matter physicists, are interested in how matter organizes itself. Again, in physics, as I said, you can study things on different scales. You can study the ultimate constituents of matter, or you can say that regardless of what the ultimate constituents are, how does matter organize itself in the large? And I am that kind of physicist. We are interested in the states of matter, changes of state from one to the other, things like gases, liquids, solids, more subtle kinds of organization like liquid crystals, organization having to do not with spatial structure, but with electrical and magnetic properties like in magnets, organization that is time dependent like in fluid flow, and so forth. And from this point of view, a flock looks a lot like a liquid crystal or a magnet, except that things are not just lined up, it's elongated objects lined up, but they're also moving. And we are particularly interested in phenomena like all these phases of matter that I'm talking about, where the organization is spontaneous. It's not that there's an external agency telling everybody to line up. It's that when you pack things, it turns out that the system settles down either for reasons of minimizing energy or for reasons of maximizing wriggle room, maximizing entropy, into a nicely arranged state, like a crystal or a liquid crystal. This is called the spontaneous appearance of order. And that's what physicists are very interested in. It's also important to realize that it's natural for physicists to be interested in phenomena of life, because life takes place because of the laws of physics and not by defying the laws of physics. Basically, in almost any situation, if you maintain a gradient, let us say in temperature or something, you produce a flux, for example, of energy into a system. That flux of energy into a system can locally create states of high complexity, high order, even though on a completely macroscopic scale, the second law of thermodynamics tells you that entropy always increases. So locally, you can create order. You feed in, if you like, organized energy, system does something with it, produces structure, spits out randomized energy. And this is, of course, what happens in all of life. We eat and we do things and we produce waste. So studying living matter, studying active matter, has to do with studying open systems. Systems different from the easy systems they teach you about in high school or college thermodynamics. In high school or college thermodynamics, they teach you about systems which are isolated and therefore have a fixed budget of energy, or systems which are a subset of an overall isolated system. Let us say this is the subsystem, this is the bath. Energy is exchanged both ways between subsystem and bath. And both of these are essentially closed systems. Both of these have a dynamics which, when things settle down to a stationary state, is invariant under a reversal of time. What that means is, if you take a movie of all the molecular events going on, you can play the movie forward or backward, and on average, you will not be able to tell the difference. In open systems, the steady state that sets in when you go on feeding energy into a system, it dissipates, and energy gets spat out, waste energy gets spat out, and you have a stationary state. That stationary state will have all kinds of events going on in it, which will look totally different if you run the movie backward. Examples of open systems are things as simple as a stirred fluid, a wire in which you maintain a potential difference and carry a current, an engine consuming fuel and running as long as you keep the fuel topped up, a planet on which sun is shining and life, like plant life and animal life is happening, or a living organism steadily supplied with food. These are all systems which are time reversal, non-invariant, because you are constantly feeding the system energy which it's using. And the general laws governing systems in a state of this sort are not formulated. They are unknown, and we explore them system by system in specific cases and try to understand them. So active matter, therefore, is the study of collections of particles, each of which is endowed with the ability to take up some energy that you supply it and convert it into work, into systematic movement. So clearly, all living systems or their energy using components, as well as many amusing artificial realizations, which I'll tell you a bit about during the talk, are active particles. Collections of active particles are active matter. And there's formally nice ways of building these equations of motion describing these systems. It's not my place, it's not the place to explain it in this talk, but those of you who are interested can look at my webpage, and there are articles on this subject on it. Now, in this first moderately technical part of the talk, what I'm going to tell you about is different kinds of random motion. One is random motion corresponding to dead particles. You've got a container of stuff held at a fixed temperature, you've got a molecule in there, or you've got a container of stuff, and rather than just a molecule, you have a slightly bigger impurity, a tiny piece of something much smaller than a dust particle, micrometer sized. But in both cases, the system held at a fixed temperature and no life going on. The particle will move around at random. In that same liquid, you can also imagine something that's alive, like a bacterium swimming in the water. All of these things on this slide will execute random motion. Okay, so a molecule in the water will sort of move persistently for a bit, but eventually randomize. A slightly larger particle will move around and jiggle around randomly and do what will look like this, a very, very random walk, of which This is a slightly misleading picture taken by Mr. Jean Perrin in the early part of the 20th century, where he took a succession of images of a particle doing what is called Brownian motion. And then he just connected the dots of those images and produced this thing that looks like a trajectory. It's actually not a trajectory, because in between any two successive points here, the particle has done much more wiggly things, as illustrated by this mathematically derived picture. Okay, so Brownian motion of a molecule, Brownian motion of colloidal particle like this, and instead the random motion of a bacterium moving through a fluid. So if a bacteria moves through a fluid, it swims straight, and if the environment doesn't look any better, it doesn't swim straight. It has a mechanism for allowing it to change its direction. So it'll go straight, which is called a run. It'll then tumble, it'll go straight, it'll have a tumble, it'll go straight, and so forth. Now, all of these on long enough timescales are random paths, okay? And they're described on long enough timescales by mathematics, formulated by, originally actually by somebody studying stock prices, and which was these phenomena in the case of microscopic particles in a fluid were first observed by 18th and 19th century naturalists mentioned here. The question is, how is this kind of truly random motion with no persistence different from this kind of random motion when you go straight for a bit and then tumble? The important difference is not that you go straight for a bit and then tumble. The important difference, it turns out, is that if you measure the velocity of the dead Brownian particle and go on taking a large number of measurements and accumulate a histogram, here I've shown it in 2 dimensions, you will get a probability distribution of velocities, which is such that if you take a cut corresponding to any direction, the most probable velocity in that direction will be 0, and there'll be a spread of velocities above 0. If you take the living thing, which has a preferred velocity, it has a little controller inside which says, if you're going too slow, speed up. If it's going too fast, slow down. If you take a cut in any direction through it, you will get 2 speeds, 2 velocities, plus a certain value and minus a certain value, same magnitude, right? If you take a cut through this, you'll get that velocity and that velocity. This is what happens to a particle running around randomly, characterized only by a temperature. This is the distribution of velocities for a system of particles characterized by a controller-determined preferred speed. Now you would say, why does it matter? That's what happens on a very small length scale. On large scales, basically these things are running around at random. Does it make a difference? Turns out it makes a big difference. If you take a collection of particles of this type, each of which has a temperature, and maybe it's a particle with a certain size, and it's running around randomly because the system has a temperature, and you study that collection as a function of increasing packing density, okay? Low density, you're in a gas or a fluid. Higher density, you pack, and it turns out the best way to pack is to pack in a crystalline way. If the particles are anisotropic, you can do something slightly better. You can pack into a liquid crystal. If you take many particles of this type, each of which has a strongly favored speed, and increase the packing fraction, if you take particles of that sort that, let's say, don't want to bump into each other, have some gregarious tendency to be near each other, and either for packing reasons or for behavioral reasons, have a tendency to point in the same direction, you get something totally different. What you get is that at low densities, they're pointing randomly. At high densities, they all point in the same direction and move in the same direction. It's called a flock. In fact, it's a slightly more interesting state. What you get is not just a flock. You can get something that's random and dilute and moving randomly, or you can get a kind of striped phase all moving together, or you can get a homogeneous phase all moving together. Okay, so flocking is what happens when you have large numbers of particles of this type. Crystallization or liquid crystal formation is all that can happen if you have a large number of particles of this type. Dead particles organize into static structures which can be ordered. Live particles with preferred speed organize into coherently moving structures. Okay, you can see these in experiments. These are arrows corresponding to the speeds of live cells extracted from fish scales and placed on a glass slide at different numbers. You increase the number of cells, and all of a sudden they spontaneously go into this moving state. This is real experimental data from a group in Hungary. So these are flocks. So as a function of crowding, dead stuff crystallizes or forms a liquid crystal. As a function of crowding, live motile stuff forms flocks. Even if the particles have no tendency to align with each other, suppose you've got a bunch of round particles that, a collection of round particles, each of which has a tendency to keep moving in some direction. If you pack a bunch of those, if you start increasing the concentration, what happens is, here's one particle moving along, here's another particle moving along, there's another. You can imagine that they all enter the same region and they're all sort of at loggerheads going at each other. So what ends up happening is that because it takes time for random noise to change their directions of motion, they end up condensing. So here, if you have dead particles moving around at random and you increase the concentration, they form some kind of slightly dense, slightly homogeneous system. If you have live motile particles running around, even with no tendency to align, they end up forming condensed. They end up undergoing a phase transition, that is a change of state, from a homogeneously distributed system to a system of dense blobs of droplets. They condense even though they don't attract. So these are the kinds of ways in which collections of autonomously driven particles that are trying to move, are different from dead particles. So that's one of the places we came in. We got interested in creating experimental realizations of these particles and testing theoretical predictions that we ourselves had made. So there were many people involved in this. The two professors who were involved in it were Ajay Sood and Narayan Menon. And various of these people were our joint students or Ajay's student, all the names being mentioned here. It began with Vijay's PhD work. And it was in a very, very primitive looking system, an industrial magnetic shaker. This is about this size of 15 centimeters, that top plate. Particles placed inside a little geometry like this. So this is the top view. This is the side view of that geometry. The particles are about half a centimeter in length, various shapes, rods, tapered rods, one side tapered rods. The thickness is slightly more than a millimeter. This system vibrates up and down. And if you have a particle like this placed in this gap, as the system vibrates up and down, the particle tilts slightly. And each time it tilts, it comes down and it ends up walking. So the particle ends up walking like this. So we can create an elementary energy conversion device in the form of this tapered particle, which takes up the vibrational energy of the surface it's lying on. And because its two ends are different, and because it typically comes down the fat end, and because of static friction, it ends up being impelled along its length and it walks. On long enough time scales, it changes its direction. So in long enough time scales, it will execute a walk that looks like one of these walks. One second. Like one of these walks, a persistent but ultimately random walk. That is, it ends up doing this kind of behavior. Depending on the geometry of the particle, you can even imitate run and tumble behavior as seen here in this movie by Nitin Kumar. This is again a dead piece of metal on a vibrating surface. It moves persistently for a while, but then changes its direction. And so we studied this phenomenon. One of the things we did was to study collections of these tapered rods in the middle of a bunch of beads. So you've got two kinds of particles in this picture. You've got rods and you've got beads. You've got a funny boundary to keep particles from accumulating. The rods and the beads are running around. The beads, of course, do nothing in this picture. They just jump more or less in place. If you take this same system and take the same number of rods, but increase only the number of beads, all of a sudden, the rods talk to each other via the bead medium, and they form an organized structure. They form a flock. So in this system, you sprinkle a small number of these pointy tapered particles and a much larger number of the beads. As a function of the concentration of beads, the system goes from this behavior, random motion, to this behavior, ordered motion, if you just wait a little bit, spontaneously. And if you repeat the experiment, sometimes they'll go around this way, sometimes they'll go around the other way. If you recreate this experiment in the computer by faithfully reproducing all the mechanics, but in a geometry in which there are no boundaries, where if a particle goes off an edge, it enters the other edge, then what you find is a perfectly homogeneous ordered flock. So these particles, the rods move the beads reorient the rods, and you get a flock. So this is one of our contributions to this work, is showing that you can artificially realize flocks in systems which are homogeneously suffused with energy in the form of vibration, provided the particles structurally are capable of taking up that vibration energy and converting it into motion. And you can study this, as I said, as a function of the packing fraction of beads, and you get a true phase transition, a change of state from random to oriented via intermediate states in which they get more and more and more oriented. A tiny number of autonomously propelled particle, a motile minority, is able to mobilize a whole majority. As you see here, not only the rods, but the beads are also moving. We don't know if this idea has applications, but we think it should. We haven't managed to find something patentable here, but it's a beautiful idea, and we hope we eventually will. Another phenomenon that takes place, again, only in systems of motile, that is autonomously self-propelled particles, is trapping. Supposing you have the same experimental geometry. In the middle of that geometry, you placed an obstacle. The obstacle happens to be shaped like a V. And, excuse me, if you had sprinkled a bunch of random walking ordinary Brownian particles in this geometry, if you sprinkled a bunch of beads that just sort of shuffle around at random, you would have, at all packing fractions, you would have got a homogeneous distribution of particles all over here. The presence of this boundary, this obstacle, would have merely created a zone where you can't have particles, and everybody would distribute at random. Here, as you change the angle of the V from large to smaller, all of a sudden you cross a threshold at which the motile particles go into the V and don't come out. So even though self-propelling motion is random in these systems on long time scales, the collective effects of self-propelling motion can be such that you end up trapping particles. So it's another phase transition. So I told you about 3 phase transitions in these self-propelled systems. One is flocking, 4 actually. The other is flocking even without making contact, because they can communicate their motion through an intermediate medium of beads. The other was, which I showed you in the early picture, self-propelled particles with no tendency to align, still condensing into blobs. And this is kind of a combination of that condensing tendency and enhanced by the presence of an obstacle, which is called, and it ends up being trapping. Now, one more fun thing that we have done is to ask what happens when the medium is a crystal. Just tell me, by the way, interrupt in case you think I've talked for too long and I have to stop. When the medium is a crystal instead of a fluid, so when the bead medium is at high enough packing fraction that the beads are spontaneously organized into a crystalline packing like this, then what happens? Then if you put in one of these rod-like particles, as it moves, unlike in the fluid where it drags the beads, in the crystal, it plows through the medium, but it doesn't drag the beads. The beads stay where they are. And then the question which Rahul Gupta asked is what happens? And it turns out what happens is that when one of these particles moves in the crystalline medium, the medium doesn't flow, but the medium distorts in a rather subtle way. And if you put 2 particles in this medium, those particles talk to each other. So if you send one particle in from here and you have another particle there, so the red particle is coming in from here, the blue particle is over there. So here's one particle, here's another particle. It turns out this one, a particle as it moves, leaves a trail of distortion which is very strong behind it. And in front of it, that distortion, it turns out, for physics reasons, is highly screened, so much so that a particle in front doesn't know the particle behind is approaching it. The particle behind senses the trail, the distortion trail of the particle in front, so you can get stealth, pursuit, and capture, which we predicted in the theory and reproduced in a detailed mechanical simulation as well as in the experiment. There's a lot more to it, which is in this paper, which you can read about on the archive if you like. And then just for fun, you can ask what happens if you put many motile particles into a rod-like medium. It's kind of fun to watch that, so take a look. Here's many. You can see they turn towards each other. It's not that they move laterally towards each other. They turn their heads in response to the distortion they're creating and find each other and then stay together and go along. This is rather cool. We haven't studied in detail the many particle behavior, but this movie is one indication of the kind of thing that can happen. Lastly, for this part of the talk, still talking basically about dry active matter. Active matter on a terrain where the terrain itself is just a vibrating surface. Supposing you had particles that are elongated but don't have a difference between head and tail. Okay, if you take these like these little long ellipses that I've drawn here, suppose you have a bunch of particles of that sort, what happens? Let me first show you what those particles do individually. This is again from an experiment. This is from Vijay Narayan. Same vibrating surface. You've got elongated particles lying on the surface. Notice that these elongated particles, some of them may be motile and actually running along, but most of them are shuffling back and forth primarily along their length. They're doing three kinds of random things. They're moving along their length, they're moving a little bit laterally, and they're turning. Note, however, that the amount of energy in their moving along their length and moving perpendicular to their length is very different. If you had a gas molecule of any elongated shape and it just had a temperature and therefore was moving randomly, it would have as much kinetic energy for moving this way as for moving that way, as for moving that way anyway. That's what is called Equi Partition, a concept which you may remember from high school or college thermodynamics, statistics, thermal physics. What you see is these particles are defying Equi Partition. These rod-like particles placed on a substrate and being energized by collisions in which they dissipate the energy each time are doing something very different from Equi Partition. Most of their kinetic energy is in their along their length motion. This is very different from a particle at thermal equilibrium. So these particles, even though they don't have a head-tail difference and therefore they aren't traveling individually in a given direction, they are also very, very out of equilibrium. They are also active. So they have no head, but they're not dead. If you take a bunch of elongated particles and randomly moving particles and pack them, they form aligned structures. That happens even at thermal equilibrium in rod-like molecules. However, these aligned structures are interesting because if you distort their configuration, you now produce structures which have globally a difference between this end and that end. In this splayed structure, this end is pointy, that end is broad, and so the arrow is pointing this way. In this bent structure, again, there's a natural arrow pointing that way. You might expect these curved structures, therefore, because they're active, to start translating in the direction in which these arrows are pointing. This has dramatic consequences. This is what we predicted from theory. We predicted in particular that if you look at the number of particles in a given region, let us say the number on average is n, and you look at the statistical fluctuations, then that fluctuation is way larger than a square root of n. This is a big prediction we made, which turned out to be true as seen from experiments that Vijay Narayan and Narayan Menon and I were responsible for some years ago. Moreover, the same tendency for a curvature to produce an aligned state turns out to mean that if you have local structural defects in these systems, and these systems do have structural defects, but in an aligned state, you can locally have a structure in which the orientation is pointing this way here, that way here, that way here, that way here, and that way here. So points in the system in which the orientation, as you walk around that point, goes from pointing this way, this way, this way, this way, this way. That is, as you go around that point, the orientation rotates by 180 degrees, which, because these particles are head-tail symmetric rods, is a perfectly satisfactory state of affairs. There's no mismatch when you go around and come back. You go around 360 degrees and the rod orientation goes through 180 degrees. That's a perfectly good local defect. That structure has a vectorial asymmetry. That structure is different on this side from on this side. Therefore, this composite object, this local geometrical object or topological object created by this distortion, has a head-tail asymmetry, even though the individual particles don't. This other kind of defect, where if you go around, the structure rotates by the orientation changes by minus 180 degrees, gives you a threefold symmetric structure, so it doesn't have a head or a tail. We predicted, therefore, that these kinds of guys should travel as though they were motorized, and these guys should not. So here you see a defect pair. There is a plus half of this type here. There's a minus half of this type here. And as you can see from this time lapse, the plus half moves. Or as you can see, maybe more convincingly from this movie, the plus half is moving and the minus half is sitting still. So this is another thing that we predicted on pure symmetry grounds, and then did the experiment and saw that it actually came true. And this idea has turned out to be very important in the mechanics of dividing and developing biological tissue. There are many tissues in which the individual cells are elongated, and the mechanics of that tissue, the structure and the development, has a lot to do with the behavior of these things called topological defects. So that ends this part of the talk on dry active matter. I will pause here for a minute. We can have some discussion, and then we'll come back with questions, if you like.
There is a question from Pragya Arora. So she's asking, what is the role of particle shape anisotropy on the non-mutual interactions?
Particle anisotropy is not just anisotropy, but fore-aft asymmetry is essential for this particular type of non-mutual interaction. The reason is, suppose you have two particles. The only way an interaction can be non-mutual is if you can put identifiers on the particles saying that this is A and that is B. Here the particles themselves are the same, but the point is, because each particle points in a certain direction, you can talk about which particle is in front of which particle is behind which particle. If you had two particles whose head and tail were the same, you could, if you had, there is symmetric rods, then you couldn't even talk about which is forward, which is back. So you don't have that much scope for non-mutuality unless you, introduce some other structural complication. You could have non-mutuality if you had a rod, one pointing like this and one pointing like this. Then you could say this particle is pointing to the middle of that particle, and this particle is pointing perpendicular. If you have two particles like this, then even if they don't have a head-tail difference, you can label them. You can say the one particle has its middle facing the other particle's tip. This particle has its tip facing this particle's middle. You could have non-mutuality of this sort. So you need the possibility of labeling in order to create non-mutuality. The important thing is non-mutuality can't happen in particles with a pair interaction based on some potential energy. Because then Newton's third law tells you that force on A due to B is minus force on B due to A. Here the interaction is much more subtle. One particle's movement creates a strain which changes the other particle's direction. And so all of that is essential. But it's a very good question, and the vector character of the particles is very weak.
Right. So the other question is from Rajesh Ganapati. So he asked, both with regard to your application for a motile minority, which is steering an immotile majority, do you think if you have a small array of humanoid-looking robots, could they steer a large crowd, for example, during a panicky situation? Or maybe even a...
Well, I've never been to Tirupati, but I've been told that a very small number of people manage to steer a large number of people, but there they also use fences. This kind of idea has been suggested. Somehow we've never managed to develop this into a technology or a patent, and maybe we should talk more about it. Rajesh, of course, is not my intended audience. I really wanted to preach to the unconverted, but anyway, I'm glad. Thanks for the question, Rajesh.
Another question sort of thing from Dipankar Banerjee. So he says a question on entropic effects driving clustering, since packing fractions of beads are different around the rods. So there isn't a question there. So if you could expand on that, that might help.
It's not clear. It can't be as simple as that. When you try the same stunt with rods but without a head-tail difference,
right.
4 arc symmetric rods, nothing happens. They absolutely have to move. The distortion in the bead medium is produced not by the presence but by the movement of the rods.
Right.
And we have a very detailed analytical theory of this, which we can solve, and it accounts very nicely for the phenomena. It predicts what happens.
Correct. So continuing on that, I had a question. I mean, when you in the introduction you mentioned dead or alive particle, most of it was based on whether something is moving or non-moving.
Yes.
Motility was one of the primary things, and also when you said motility, and when you said performing living functions, it was primarily again the question of either motility or ordering patterns and so on.
Yeah.
The other more important thing is replication, of course, which is not there in
tall order.
These. Tall order, yeah.
Very tall order, so, but you know that Paul Chaikin has been trying to make self-replicating chains of colloids and so forth. There's been work. Zorana Zirabcic, Paul Chaikin, various people have done various attempts at self-replication, but I mean, I don't even think you can. I don't know if you can call them even proof of principle. Maybe they are kind of cute demos, but you would need, first of all, I should emphasize, the particles we talked about here are great big particles, right? Millimeters dia and 5 millimeter length. And doing anything resembling chemistry on them will be very cumbersome. You would at least need to go to the colloidal regime, and even then, you would need more. I don't know. Worth a thought, but I don't know.
Right. So the last question before we go, maybe if you go to the macroscopic scale, so predictions from the hydrodynamic theories, have they been tested in real flocks of birds, not imitated versions, but actually?
Yeah, so that's a very nice question. Work that I didn't know, there's magnificent work by a group in Rome, Irene Giardina, Andrea Cavagna, and various people. So these guys do real experimental condensed matter physics on condensed matter samples a kilometer in size, namely flocks of starlings that come at various times of day to roost on the roof of a Rome railway station. And so they have movies, but they don't just take movies. They have a massive team of physicists and computer scientists and all kinds of people and image analysis people figuring out how from their movie data to measure three-dimensional structural parameters and correlation functions. And then what they do is they write down a simple minimal theory, and they try not to fit the theory to the phenomena, not to compare the theory with the phenomenon in the usual sense, but backward to back out the, in a least biased way, say, within this class of theories, what interaction parameters in a least biased or maximum entropy way best describes the observed effects. Okay, it's a colossal challenge. They have done spectacular work on this. And what they find is that the simple model of the sort that I told you about, things aligning with their neighbors, needs one very important modification as far as we can tell, which is that the birds don't align with their nearest neighbors in a distance sense. They look all around in a line of, and align with, they seem to correlate themselves to the first half a dozen or 7 or 8 things they see all around, subject to some restrictions, independent of direction. So because birds are interacting by vision, if they look in a given direction, it doesn't matter if something is very near or farther. So the interactions in a sense are topological, not metric.
Right.
This is one important conclusion, which means if you dilate a region, you've basically not changed their interactions.
Okay.
So there are theoretical models of a non-metric, a purely topological character, which you can write down. At very long wavelengths, I'm pretty sure, actually, despite initial claims to the contrary, that the behavior predicted finally turns out to be the same. That's a technical subtlety which I can't get into here. But I think that's the point. The point is that you can apply it, and then this issue comes up. This is one major issue that comes up. There are others, but this is probably the biggest. Fish schools, nobody has really tried to apply this. People have applied flux and fluid theories, but in a regime where viscous interactions don't matter and it's all inertia, and they achieve some degree of good description and predictions. Yeah.
Okay, so there's one question from Mandar Inamdar. Have you considered examples in biology, such as organelles, for instance, mitochondria moving within cells, and will your model be applicable in these situations?
So, I mean, the problem is I don't know. So, again, in the second part of my talk, I'll be talking about active matter in a fluid medium.
Then we can.
Maybe I can come to that, because those equations, even though we wrote them down trying to understand groups of organisms moving through a fluid, they turn out to apply to the subcellular world unmodified. And that's an important achievement. That's in the second half of the talk. The fluid is important. The viscous medium is important in all those cases, as far as I know. Vijay can probably tell you a lot more about that than I can.
Okay, so then maybe we move ahead.
Okay, so as I said, that first part was about simple flocking models in which the ambient medium doesn't play a role except to the extent that we strewed those beads and they produced a kind of medium. We basically had self-propelled particles whose self-propulsion mechanism had to do with walking on a dry surface. We were ignoring the medium which helps the particle acquire motility. But we realized, in fact, our first work on the problem was on understanding self-propulsion in a fluid medium. It struck us that these flocking models were purely descriptive, not mechanical. They were based on arbitrary rules, not rules governed by the laws of mechanics. So you had, in those simple flocking models, you have an organism, it looks at its neighbors and it reorients. In practice, if the flocking is taking place in a medium, if you're moving and you reorient, you've changed your momentum. You and the medium, the fluid medium around you, have to conserve their total momentum. So if you turn, you produce flow, which moves the other things. So you need to take fluid flow into account. So we built the equations of motion of flux in fluid. So we asked, what are the simple ways of swimming? The simple ways of swimming have to do with an organism doing something to the fluid and its body moving in response to that something. The simplest are either creatures that have filaments in front that they pull the fluid with, and their body moves up, or creatures which push the fluid behind them and their body moves ahead. And these produce flows that look like this: inward along the long axis or outward along the long axis, and the opposite way in the remaining two directions automatically. So we built the equations of motion. This was the PhD work of the late Aditya Sinha, and also work we did with Yashodhan Hathwardane and Madan Rao. And these equations describe the orientation of these organisms collectively in a sort of smooth orientation field varying from point to point in space rather than looking at individual particles. We built the equations of fluid of many swimmers. Their essential physics was that the swimmers push the fluid and the fluid carries, stretches, and aligns the swimmers. And those equations looked roughly like this. Basically, that inhomogeneities in the state of orientation produce fluid flow. That fluid flow changes orientation. So you've got a bunch of swimmers. If locally they're not quite pointing the same way, some stresses will be unbalanced, that will produce flow, and that flow will reorient the orientation of these guys. That's really all you need to know from this slide. Interestingly, our equations were rediscovered 2 years later as a description not of a collection of organisms moving through a fluid, but of what takes place inside one living cell. There it's not organisms, it's biofilaments, and it's not swimming, it's the movement of molecular motors on those filaments. It turns out the same equations apply there. And this is one of the deep lessons of physics, that if two problems have the same kind of symmetries and the same kind of thermodynamic conditions, they'll do the same thing. The same laws apply based on symmetry. And so we wrote down something to understand flux and fluid. It turns out those constitute the mathematical and physical description of the mechanics of what is called the cytoskeleton, the filaments and motors inside a living cell. In that context, they call it active gel theory. And it is really the description needed to understand processes like cell division, cell adhesion, cell crawling, and so forth. So we're very pleased that our idea concocted for our amusement, more or less, turns out to describe physics that maybe is more serious than what we were thinking about. Anyway, so we did this, and among the predictions of that is the following, that basically, if you take an oriented state of these swimmers and you distort it slightly, then what happens? Let us say they're the polar types of swimmers like this. If you distort like this, then the pulling bits are closer together here and farther apart there. So they produce a flow like that. Here, the pulling bits are closer together here and far apart here. So the flow is like that downward. Therefore, in this region in between, you're shearing it like this. So these filaments, which are already pointing that way, get turned to point more that way. And you can repeat the same story. Instead, if you have pusher swimmers, which are pushing outward along the long axis, there what will happen is if you perturb the oriented state this way, it will get more pushed in the direction which you perturbed it in this case. So pullers go unstable in this geometry called splay, pushers go unstable in this geometry called bend. In either case, to the extent that you can assume that a local disturbance in the orientation produces fluid flow everywhere instantaneously, that is, if you ignore the inertia of the fluid, aligned active fluids are simply unstable. A collection of bacteria can't swim in the same direction collectively. On big enough scales, it'll always go unstable. Okay? And it'll go unstable at a rate that doesn't depend on length scale. And the reason is, if you do a little bit of elementary physics, if you have a system with a characteristic scale of stress, how hard these swimmers are trying to swim, that's this parameter sigma A, stress. System also has a viscosity. The ratio of viscosity to stress is at time, or the ratio of stress to viscosity is an inverse time. That inverse time, it turns out, determines the growth rate of disturbances at essentially any length scale in the system, as long as you can assume as long as you can ignore inertia in the fluid. So aligned active fluids are just plain unstable. And the beautiful experiments only last, well, year before last, really showing the onset and growth of this instability that we predicted in great detail by templating, by using a liquid crystalline template with some aligned structures onto which they put these active filaments and motors. And you could see the bend instability that we predicted for pusher swimmers really set in spectacularly and go from small disturbance to larger disturbance to larger disturbance, and eventually to the liberation of defect structures. This is in a group from Barcelona, really gorgeous experiments. A few years earlier, we had actually seen, in collaboration with Shiva Shankar, who was then at National University of Singapore, my then student, Ananya Moitro, showed that a phenomenon that Shiva's group was seeing, namely that when you take a cell and place it on a fixed geometry. So now this is not the cell, this is just the nucleus. The cell is much bigger than this, somewhere out there. Place it in a fixed geometry. What they found was spontaneous fluid flow taking place in the region around the cell, around the nucleus, filaments aligning and spontaneously tilting in exactly the way in those pictures, flow taking place, and that flow leading to a rotation of the nucleus. We were able to calculate the circumferential velocity as a function of radial distance, here calculated, here measured by a lot of averaging. And this is, remember, inside one cell. They were doing fluid dynamics inside an object a few tens of micrometers in size. And turns out to work beautifully, both in terms of the form of the profile and in terms of the magnitude of the rotation rate. You can see the rotation rate is rather slow. It's a few degrees per minute, but it happens and it all works out beautifully. Okay. And this self-destruction of orderly swimming ultimately leads to a state called active turbulence, which has been the focus of huge studies over the past few years. But our recent interest was in the following. Okay, we've talked about flux in fluid. We said, flux without fluid and flux with fluid are radically different. And you put in fluid dynamics and you found that all this beautiful flocking fluid dissolves into active turbulence. However, stable flux in fluid most certainly exist. After all, they're fish schools, right? So now, of course, you can say that very different physics operates on the length scale of fish schools from the length scale of bacteria. On the other hand, the same equations of fluid dynamics operate on the equations length scale of fish schools or on the length scale of bacteria. So what's the difference? It's clearly the difference is clearly the different parts of those equations of motion are important. In fish schools, it's all about inertia. In bacteria, it's all about viscosity. Microorganisms go on moving their filaments in order to move. If they stop moving, they come to a halt practically instantaneously. As you know, if you've tried to swim, if you kick, you can keep going for many body lengths. So these are the two different kinds of swimming, but it's the same equations. So rather than go to the length scale of fish schools and try to study fluid dynamics directly there, supposing we say, we'll start with these equations of fluid mechanics where we ignore inertia and timidly put in a little bit of the inertia of the fluid. What does that mean? What that means is the following. What we studied with Ryan Chatterjee, now at Pittsburgh, Aditi, Navdeep Rana, and Prasad Pedlekar at TIFR Hyderabad, was to say that let's introduce a comparison. Let's not forget inertia altogether. Let's note that actually if you include inertia, the instability that I talked about actually has a time scale of onset which depends on length. And that time scale is given by a certain combination of the active stress and the mass density of the fluid. Okay, so forget about all the maths here. Just look at the letter R and look at these words here. You can construct a unitless object, which is the ratio of two speeds. The rate at which the organism is swimming, the speed at which the organism is swimming, and the speed at which the instability sets in. Okay, turns out if you do the maths, there are these two speeds. And the approximation in which you ignore inertia assumes the instability sets in at like infinite speed. It sets in instantly. Strictly speaking, it doesn't set in instantaneously. There is this ratio, which is this letter R, which is a square of swim speed over instability speed. Forget about all the other parameters here. They don't really matter. If you do the maths, the same problem, then it turns out it really matters whether this quantity is really much less than 1 or of order 1 or much bigger than 1. It turns out if you swim fast enough, you can outrun the instability. So what you end up finding is that the following. Suppose you consider a perfectly aligned state and now disturb it slightly with disturbances that vary with a certain length scale in space. Okay, this axis is 1 upon that wavelength of the disturbance. Q is what is called wave number. It's the inverse of the wavelength. This is the rate at which that disturbance grows. If this quantity is above the 0, it means the disturbance is growing. If it's below 0, that is, it isn't a growing disturbance. It's a decaying disturbance. What we showed was that depending on whether that parameter R was 0 or small or somewhat larger or even larger, you either get a disturbance that grows at all length scales up to the length scale at which the interaction that promotes local order sets in, or it grows out to very large length scales but eventually goes to 0. And if you zoom on this bit, it looks like this. Or if you go to slightly larger inertia, that is slightly larger self-propelling speed, then it grows much more weakly. This, at, if you like, when R is small but non-zero, at very long wavelengths, the disturbance grows at a rate proportional to 1 upon the wavelength. If the swim speed is larger, the disturbance grows as 1 upon the square of the wavelength. If the swim speed is even larger, the disturbance doesn't grow. So you can actually have flocks in fluid that are stable. And the full story is that if you study this parameter, don't worry about it. If you just study the behavior as a function of swim speed, here represented by the parameter R, then down here is the physics of the always unstable flock in fluid. As you increase R, you go from violently unstable to weakly unstable to not unstable at all. And what you find there is that if your system is in the regime where the growth rates are proportional to 1 upon the wavelength, you start with an aligned state, you disturb it slightly, the disturbances grow and the system dissolves into a total mess of spectacular defect structures that look like this. If you're in the regime where the aligned state is still unstable when perturbed, but not too unstable, the disturbance grows slowly. That disturbance, it turns out, grows for a bit, but then something nonlinear cleans it up, and the system stays in an on average aligned, although slightly noisy, slightly disturbed state. So two kinds of defect states, two kinds of unstable states. One where disturbances grow radically and the system goes violently unstable. That happens when inertia is very small, when swim speed is very small. At slightly higher swim speed, system is still nominally unstable. The equations predict that a slight disturbance will grow. The system grows but eventually rights itself and the system stays stable. And so as a function of swim speed, you go from defect turbulence to noisy but ultimately ordered to absolutely ordered state. You can measure the amount of order, how well aligned these little unit vectors attached to the particles are, as a function of the parameter r. At low values of r, that value is consistent with 0. Across a threshold value of r, the amount of order all of a sudden sets into a non-zero value. If you measure how correlated the movements are across the median, the correlations between the alignment here and the alignment there as a function of distance between these 2 points decays with distance exponentially. Rapidly here, as you increase r, more slowly, as you increase r further, more slowly. So as you go from here to here to here to here, you go from very disordered, rapidly decaying correlations to less disordered, more slowly decaying correlations, eventually to an ordered state. The length over which correlations decay, which I've plotted the inverse of here, as a function of r, which I've plotted again as a function of 1 over r, as you decrease 1 over r, that is, as you increase r, 1 upon the length decreases, that is, say the length increases. The range of spatial correlations grows as you increase r from small values to large values. So you actually have what is called a phase transition, a change of state from random, disordered to nicely ordered as a function of how fast the organisms are. Nobody has yet really looked at an experiment in which this can be tested, because what you need is organisms that are not as slow swimming as bacteria, but kind of swimming at a moderate speed, maybe millimeters per second rather than micrometers per second, and of slightly larger size, maybe millimeters rather than micrometers. And you need a knob you can turn to tune this speed and watch this transition. You can do this in computer experiments, but I'd like to see it done in real experiments. It's not happened yet. But this completely changes the game. Rather than viewing flux and fluid as irredeemably unstable, you realize that this wildly unstable bacterial turbulence, active turbulence state is just one end of a much richer range of behaviors, which include a phase transition from a randomly moving state to a coherently moving state, just as a function of swimming speed. And that ends this part of the story.
Another question is, it's another interval. Should I simply end the talk and take questions, or spend a few minutes on the last bit? I would suggest we have if there are questions, I'd suggest we have a discussion now. And if people are still interested and there is time, I'll talk about the third one. Is that okay?
There aren't any questions right away from the audience,
Okay.
but I could ask one or two, or you could go ahead and then I can continue later.
No, well, you can. Let's do questions again. I think there was a large amount of material. So if you have some comments or questions, we may as well go ahead.
So one of the things that I wondered about when you showed the rotation of the nucleus, right? So the the rotary motion really comes because of the filaments which are outside the nucleus. These are things which are sitting in the bulk of the cell. So presumably, is the chirality of the filaments important, or is this something which will be seen in even?
In Shiva's experiments, it looked as though you got clockwise and anti-clockwise rotation about equally often if you repeated the experiments. Since absolutely all biological matter has a handedness, all biological matter is chiral. it's entirely possible that if you did a very thorough study, you would find that the instability favored one handedness over another. Other realizations of the same kind of instability in layers of elongated cells, as well as in some experiments from Weizmann by, who's the guy here? Anyway, you know him. Beshatsky. There they tend to, different kind of experiment, not looking at nuclear rotation as such, but looking at circulating flows inside the cell, in that case, and in epithelial, there is monolayers, dense monolayers of elongated cells. There also they see this spontaneous slight misalignment and corresponding flow. In all of those, they tend to see one sign, one-handedness only. So you've got a layer of cells like this, and you always see the circulation this way on one side and this way on the other side, and not the other way. So imagine you've got a bunch of cells. You can't see by looking at them that there's some handedness. They look just like elongated rod-like things, but there's invariably that this side is going like this. So there is very likely there are subtle chiral effects even in the case we talked about. We haven't gone back to these experiments, and so at this point we don't know. To the best of our ability, it seemed like both-handedness.
Right. So to continue, I mean, is that useful in a biological sense, or is this just
no idea? It's very, very puzzling. In order to see the instability in that, you see this spontaneous circulation in the cell had to be placed on a well-defined geometry. So it would be placed on a disc-like geometry, so it had a well-defined boundary condition. The edge didn't distort. You could then see it. Something similar kinds of spontaneous rotation of cells is often seen during the development. Spontaneous rotation of nuclei is often seen during the development process. Nobody has been able to tell us if it's any use or if it's a weird byproduct that nobody knows the reason for.
No, but for chiral things, it is known that maybe there is some implication for left-right axis establishment.
Yeah, absolutely. So in development, in the flows associated with the development of the organism, as on which you are the expert, clearly, establishing bilateral asymmetry in the organism requires flows with a preferred handedness, which seem to be dictated by molecular chiral properties, according to work that you've told me about or that you are part of. I don't know in this context if that's the case, because what we saw was really inside one cell.
Right. So there's one question from K. Venkatramana, and he asks, will they not collapse in disordered movement? So I don't know what is
which ones? Who are they?
Yeah, I'm also not. I asked him. I hope he responds. I presume it's the nucleus, but I'm not very sure. Or is it really about the flocking birds? I don't know. The question is just, will they not collapse in a disorder?
If he likes, he can type for the...
Yeah. He's not responding.
Oh, collide. Yeah, okay. He's saying collide, not collapse.
No. He's saying, will they not collapse?
No. Look at the updated...
Oh, yeah. Collide. Yeah.
Collide. So that depends. The point is this. Whenever you've got... If you have this sort of chaotic movement in a fluid medium, in a viscous fluid medium, then objects that start to move towards each other will never really collide as such. There is, lubrication forces will tend to make them get more and more slowed down as they approach each other, and typically they will end up moving past each other or circulating around each other, depending on how they come at each other. So that a collision in the viscous hydrodynamic regime is a very squishy, soft thing. Okay. It's not a whack like that.
Correct.
That's really what happens. So that's a nice question.
Yeah. So since you spoke about turbulence, I just wondered, this is not the turbulence that you'd see in your bathroom, for instance. This is a different kind of...
Right, yeah. So it's called turbulence in the sense that the flows are complex and chaotic. It is fluid flow of a complex and chaotic character. There are many important differences. When people study turbulence, normally you've got to flow through some, flow in a geometry in which the energy input is from the boundaries because of a forcing. Either you maintain a pressure gradient, in which case and you got let us say a wind tunnel or something, and the gradients are being forced by the fact that you've got a boundary at which there's no slippers, and you get energy forcing. Here, the forcing is itself present everywhere in the fluid. Right? Because each organism that is inside the fluid is doing the forcing. So it is that type of turbulence. And secondly, the control parameter is the comparison between this spontaneous growth rate that I told you about, which is ratio of active stress to viscosity, and a spontaneous and a natural relaxation rate of the orientation, which is dictated by a collective elastic constant governing how the packing leads to okay. Basically, imagine you've got a bunch of elongated things which are doing a bit of Brownian motion and are packed, and imagine that they can't swim. Imagine they're just dead Brownian particles. That system at high enough concentration will form a liquid crystal. That liquid crystal will have mechanical restoring forces if you distort its alignment. Those will give rise to restoring torques. So you've got a destabilizing torque from the instability, restoring torques from the elasticity,
right.
And the ratio of those two actually is length scale dependent.
Yeah.
That is the square root, the ratio of the elastic constant to the active stress. The viscosity actually drops out. The ratio of the elastic constant to active stress is the square of a length.
Yeah.
That length, what that means ultimately is the instability that we talk about is seen only on scales bigger than that length.
Okay.
On scales smaller than that length, it acts like a more or less ordinary liquid crystal.
Okay.
Of the sort that people have been studying for many decades. And then what we have shown is that even that is mitigated by inertia. And on big enough length scales, you can. So.
Okay, so for there are no more questions, maybe you could take the third part and do a little bit.
Okay.
And then we could come back if there are more questions.
Okay. Right. So next slide. Yeah. So I think this part has no movies anyway, so it's great. So another kind of artificial swimming system. So this is still active matter I'm continuing with the theme of active matter in a fluid, but in a very different context. This idea actually, in various ways, goes back to old ideas in colloid science, as well as old ideas in biology, where people suggested that you could have stresses generated by ionic imbalances that can create a swim. Anyway, it doesn't matter. Supposing you have a glass of water with some hydrogen peroxide. You know the hydrogen peroxide is only metastable. That is, if you disturb it too much, it will break up into water and oxygen. But if you don't disturb it, it will stick around as hydrogen peroxide. You also may know that you can catalyze the breakdown by putting in a bit of platinum. So the group Vaishnav and Sen at Penn State took particles of the sort that you see on the screen here, one end, half of which is coated with platinum, and put it into an H2O2 solution. What will happen is that at the platinum part, peroxide will be broken down into water and oxygen, and at the gold part, it won't, or it will be less. I mean, I'm oversimplifying, but basically, if you maintain a load of hydrogen peroxide in this fluid, and you put this particle into it, then along the surface of the particle, you have a compositional imbalance. So along the surface, there is more H2O2 on the gold side than on the platinum side. Imagine, don't even think of it as H2O2. Imagine it's just a fluid in which you have more little granular particles, little solute on one side, one part of the surface than another part of the surface. Whenever you have a solute gradient, you will drive an osmotic flow. You know about osmosis, right? If you've got more solute impurities here and less there, then flow will go from, if you have a membrane that's impermeable to the solute, then flow will rush in from the solute poor side to the solute rich side. Here the idea is you don't have any membrane. You maintain a high solute concentration by this catalysis. So you get flow along the surface of this particle. And that flow in this case, I think, will be from the platinum side to the gold side. So that means this object will spontaneously create a flow along its surface, very much like the flow that a ciliated microorganism like paramecium or something will create. It will create a flow in a thin layer along its surface. So it will swim platinum side forward. So as long as you keep maintaining enough hydrogen peroxide near this guy will keep swimming and will create trajectories like I've shown on the right over there. Those are not Brownian motion. They're very, very correlated, very organized swimming. Presumably, if you made many of them and packed them and they were long enough, you might even form living liquid crystals. I don't know. They don't seem to have done that. Next slide, please. Next slide. Yeah. And here you can go to the next slide. So this is the theory of this is worked out by Golestani and al. Our interest was in whether this object could imitate slightly more sophisticated functionalities rather than just swimming. Okay, can it sense a gradient? Supposing the object, the gold to platinum axis is pointing this way, and supposing there's a gradient in hydrogen peroxide that way, can it turn to point its nose that way and swim that way? Or is a gradient in some other chemical, can it turn away from it? Can you make it do the analog of what in the bacterial world is known as chemotaxis? So can it sense? So this is the idea. This is part of Shurapriya's PhD work. It is work done along with Ramin Golestanian, and we've been playing with this for a while. Next slide, please. And it turns out you can design particles with a variety of responses by designing the pattern of the catalyst coat and also the pattern of the pair interaction between solute and surface. There are two different things. One is where the pattern of where the catalysis takes place, the other the pattern of how the product particles interact with the surface. Okay, and you can make them align to point in the direction of more fuel, for example. And we have quantitative criteria for exactly how to do this. Go on, next slide. And now you can imagine a collection of such particles. You can imagine one particle will modify the solute cloud around it. Another particle will sense the resulting gradient of solute. And depending on the type of particle, you can make these things reorient towards each other, reorient away from each other. If you have just two particles, because this is governed by a diffusion equation, where if you have a source or a sink and nothing else interrupting, stuff decays is one upon distance. The interaction can be quite long ranged. So you can get really cool effects in this system. Next slide, please. You can imagine if you have a fixed source, you can create situations where the source can trap a particle, where the particle can come in, scatter off the source. You can create things like funny orbits. Next slide, please. Yeah. And so just for fun, we asked what kinds of dynamics you could get if you had two such particles. So you have a uniform medium of reactant, and you have two particles in it, and each one, by virtue of its catalysis, is modifying the reactant and product profile in its vicinity. That affects the other particle. You can create quite spectacular sort of pair dances. We haven't thought very hard about what kinds of applications to do with this, but other people seem to be taking it up with some interest. The other fun thing about this system, if you go to the next slide, is the collective behavior. If a large number of these guys instead of just two, then as a function of the two axes here, the vertical axis is how well the system reorients in response to a gradient. The horizontal axis is how rapidly it proceeds along a gradient. And as a function of that, you can get an astonishing range of behaviors, depending on whether fuel is abundant, in which case all the effects are limited just by how fast the reaction takes place, or fuel is low, in which case the dependence of the reaction rate on the fuel concentration is important. You get different kinds of phase diagrams in which, because of the 1/over distance nature of the interactions, you can produce imitations of gravitational phenomena, electrostatic phenomena, and a whole host of more complex pattern formation effects. You can read, those of you who are interested in the technical details can read about this. Some of these phenomena have now been seen in sort of computer experiments where all the microscopics are put in like in an experiment, and they're able to see spontaneous oscillations and things of the sort that we predicted. So it's been rather fun. Shurapriya, I think, is doing some more work on these things. I myself have not been lately. So I didn't want to say any more. I'd like to end at this point. I'd be happy to go back to any part of the talk you like and answer questions. Thank you. So last slide, yeah, thank you. Yeah. This is just my publicity summary. I hope I've convinced you that it's useful to think about biology. Think about and imitate biology through physics, and I've given you all kinds of examples, and it's a nice area for a theoretical physicist like me to play, and maybe it'll be useful. Thanks.
Thank you, Sriram. So far, no questions, but I guess they might come in. So, okay, there's one. Okay, there's a couple of. So there's a question from Subramanya. So can this collection or steering mechanism be used for cleaning our rivers, for instance, at least for some pollutants?
So I think the problem is that on that scale, you probably need to work with particles and not so much in the colloidal regime as. No, okay, actually, let me actually backtrack a little. The idea of using microswimmers to enter into a domain of fluid channels or other such environment and carry out functions is a very important one. That is indeed the motivation for working in this area. There are groups working on it. On the Indian scene, the most prominent is Ambarish Ghosh in the Center for Nanoscience and Engineering at IISc. So he has, most of his particles are not strictly self-propelled and they're not chemically propelled. They're magnetically actuated. They have a shape and they impose rotating magnetic fields and make these guys move. But he's also doing some things on more true swimmers. And so whether on the scale of a river this idea will be useful is not so clear, but in a sort of in a biomedical context, we think these ideas are indeed important and people are putting a lot of time thinking about them. And in fact, there's even an initiative at IISc on active matter and robotics precisely with these kinds of ideas. And Ambarish should be glad to talk.
Okay.
Thanks for that question.
Yeah. So the question from Manisha Nanda, she asked, in your model for turbulence, are you assuming that the boundaries are rigid? And how would that apply to biological systems where cell membranes or tissues are soft and flexible?
Very good question. I don't know about, okay, first of all, our calculations were done not only in rigid boundaries, they were done with no boundaries for the most part. That is, they were typically done in what are called periodic boundary conditions. I think the question of active flows in systems with deformable boundaries has started to be explored, but we haven't done any work on it. That's it. So I don't know about, the point is, if you're looking at flow on the scale of large blood vessels, then many modifications are needed to what we're talking about because inertial effects are very important in those situations. Flows through capillaries, presumably, that's not the case. But the other thing that's probably important in flow in the vasculature probably is also the actual finite size of the red blood cells. So you've got macroscopic solute in there, which itself deforms. So, but it's a valid worry, and it's not something we've done much of, but some work exists.
Right. Just to continue on that, I mean, there are studies where, for instance, people look at the stresses developed on some surface and use the stresses, the cytoskeletal stresses, to actually look at deformation of the cell or the tissues.
Right. So instabilities, I mean, these things like, formation of villi or other, so the groups at Curie and Dresden have certainly been looking at those problems.
Right.
Or
even something like even the cell division, how do you use the cytokinetic ring to actually deform it into a peanut shape and shape transformation?
Yeah. So yeah, that's true. I didn't mention that work. I sort of concentrated largely on our work, but yeah, cytokinesis itself has been very nicely understood in this context. For example, and there indeed you have to look at the deformation of the entire object in which the flow is taking place. Yeah, so, and I guess the point is, Vijay, again, the kind of studies you guys do in general in development involved.
So Manisha has a follow-up question. So regarding the rotation of the nucleus, Shiva's work that he showed. So what happens if you have multinucleate cells? What happens to the direction of motion, direction of rotation?
It's something that we need to calculate. I mean, the thing is that in that geometry, you'd have to see what is the dominant instability mode that kicks in. It's an interesting question, actually. I hadn't thought about it. And now that you ask it, maybe we will go back and think about it. Meaning that I think it's a solvable problem, but it's technically very tricky because the nuclear rotation it's now a moving boundary, actually.
Correct.
And at the level of one boundary, it's okay. What you do basically is we didn't put in a physical boundary, we put in a viscosity contrast.
Correct.
So we would have to put in a patterned viscosity contrast and ask how the instability kicks in. Interesting question. Maybe we should look at it.
So I had a question. So for example, the last part of the story where you showed the work with Shurapriya. So the cloud that is generated by the movers themselves sort of acts like an effective medium through which it can interact with the other cloud. I wonder if this has some implications for cell signaling and all.
Possibly, I know that. In fact, one thing I forgot to mention: Madan Rao and Jitu Mayer have used the general ideas of active hydrodynamics in understanding compositional statistics on the cell membrane due to active transport. And Madan has often pointed out that those ideas could lead to offer interesting signaling possibilities in a membrane context. But more generally, also, I dare say, I mean, that is why we're interested, but we haven't pursued it as a specific modeling problem in a specific context. But yes, I think
right.
Could. Likewise, the motility through elastic medium and so forth.
That's right. Okay, so far no questions. So maybe you can just speculate on a broader thing. This is just me asking you about how this field of physics and biology, or how physicists entering study of living systems will really be a fruitful thing, and how it might flower.
So actually, what I wanted to say about that goes back historically, long before any of us were looking at these problems. Physicists have always been interested in biology. There was kind of brief derailment of that broad natural science effort because of the sort of the heroic period of modern physics with quantum mechanics and all these things happening, where possibly the need to acquire new knowledge, learn new mathematical structures, drew people to focus more on sort of what we might call high theory. But even many of the high theorists were very interested in these kinds of problems. There is a very great book, very beautiful monograph called What is Life by Erwin Schrödinger. And much earlier than that, there is this gorgeous book called On Growth and Form by Darcy Wentworth Thompson, who points out that the shapes and structures of living things are strongly constrained and dictated by mechanical laws, mechanical forces, fluid flow. So that culture is actually very old. And in fluid dynamics, for instance, there's a very, very robust, sustained culture over the past 100 years of people studying these problems. So that tradition was already there in the physical sciences and the mechanical sciences generally. And recently, I would say we are not at all the people to look at it. We look at groups at where Vijay did his postdoc, for instance, with Franklin Sherman Company, or Madan Rao and Jitu Mayer. All these people have entered the field, immersed themselves in biology while not losing their physics roots, and made very important contributions. So where it's going, I think, will depend. It'll depend on a bunch of things. I mean, if you want, you can ask what would be the best way to go. I think the best way to go would depend a lot on how people get educated. So it's one thing for people, so mid to late career people saying, I'm going to work in this problem. Clearly, what you want is you need a new cadre, right, of people whose education has both biology and physics at comparable levels in it, which means you should not release onto the world a large number of people who learn biology without learning physics and maths, or learn physics and maths without learning biology. The newer science undergraduate programs in the country are certainly very aware of this and are doing the right thing. In lots of places, in lots of universities, you see biological physics courses. If you look at the biology literature, there is a small but not negligible fraction which is seriously informed by physics, not only in the sense of experimental tools and techniques, but general theory of the sort that we talked about. And of course, as Vijay knows, there are many labs in the world where this is sort of the primary enterprise, and physicists and biologists are seriously engaged with each other. So I think the point really is, for real success, you need that cadre to grow. And I think India has been a little late on this, but I think we're doing it. So time will tell. I have to confess that I have sort of sat at the edge and just stuck my toe in the water occasionally and never done it for real. But it's gratifying nonetheless that the equations we wrote. I mean, my approach has always been to ask some very general question. What must the equations of a system of such and such sort necessarily look like on symmetry grounds? If you do that and you think about an interesting problem, you're likely to produce equations of broader relevance than you thought about. And it's gratifying that that happened to us. But I didn't take the next step and plunge completely into biology. I sort of stayed largely in my safe zone. But I think our work has had influence and has influenced other people to do it. I think it's now a successful enterprise generally, but it needs people.
Thanks, Sriram. Thanks very much. I hand it over to Sushila now.
Thank you very much. This was an absolutely fascinating session. Sriram, when I heard you first speak, probably about 3 years ago, when you had addressed the students at our Rotary, and I was so fascinated and caught up with this topic and the subject and the research that's been going on. Obviously, much has happened in these 3 years, and I could see that through the duration of the talk. So thank you very, very much for so readily accepting to speak to all of our folks at the IIT Alumni Center and all of our audiences. Today, just to summarize a few points, today we saw, through the presentation, we saw basically 3 parts, looking at active systems in the flocking and movement in dry systems, liquids, as well as in chemical media. We got a very detailed understanding of what happens in each situation. So just to kind of summarize, open systems, in open systems, we see spontaneous emergence of order. And then again, Sriram took us through some basic physics concepts like condensation, but talk to us about what happens in systems that are in a sense alive. What are the differences? What happens when you look at these ideas in active, when there are active matter that is at play? We talked about and understood about phase transitions in active matter. We saw colloidal systems and understood that when the medium and the particles interact, you have a different set of things that happen, different set of outcomes. The idea of flocking, the concept of the flocking control parameter, and thus bringing it all together into a systematic understanding that allows systems to be built and predictions to be based, to be built based on these models. And some of these predictions can be applied in many situations, and Sriram talked to us about many such examples. Another example of where this today, what we saw today was again another example of where there is a convergence of different disciplines of science. We've been seeing this and hearing about this theme of convergence, I think, through the last year. You know, so many interdisciplinary projects have been taken up, and many of the solutions to big problems are interdisciplinary in nature. And we saw how this whole science is, again, the thinking is coming from looking at what would traditionally have been in different silos, and that I think is absolutely fascinating, because this is one of those completely basic, probably we're looking at what to my mind looks like a new physics, and how the thinking came from looking at what one would not have looked at if we had looked at traditional science the way we were taught it much earlier. And then there are questions that arise like, can motile organisms sense the gradient and move accordingly? Can catalysts be defined which will cause certain types of movement, certain kinds of flocking behavior to take place? So, there are lots and lots of open questions, but as we saw from some of the questions, people are already thinking about how new applications can be, the science can be applied in new places. In basic things, there are big problems that have not been solved till now that we are looking at, So there are a lot of, it's very interesting that we are already able to start thinking about how to apply this science. So what we looked at today was collective behavior as a completely different way of looking at things, rather than looking at it as a sum of individual behavior. And that to me was sort of the essence of this whole new science of active matter. There is plenty of opportunity. So if youngsters or people or young science students are listening to this, you can see it is so exciting that this whole new field is opening up. Even the general laws have not been defined, as Professor Ramaswamy said. And so there is just so much of opportunity for someone who's looking to take up physics, and we hope there are many who will take up their careers in science. So once again, thank you, Sriram. This was absolutely fascinating. It's a pity that, that the bandwidth was not okay, but we'll work around that. And Vijay, thank you so much for, again, being so readily accepting to take this up and doing a wonderful job of moderating and bringing out many new nuances of this talk. So thank you to both of you, and thanks to our audience. We will be posting this recording up in the IITACB YouTube channel. Please be sure to look at that, and in 2 weeks' time, see you with a new edition of our webinar. Thank you.